This video is about the Normalize operator. This operator changes numerical attributes to have new descriptive statistics. This means that the minimum, maximum, mean and standard deviation are all changed. This is vitally important when performing some modelling or investigative analysis, because some models require all the attributes to have the same scale. So for example, k nearest neighbours, linear regression, they can be profoundly affected if you get the normalization wrong. And of course there are others. General rule, normalization is important. So we'll cover some parameters to the normalize operator. These are the Z transformation, range transformation, proportion transformation and interquartile range transformation possibilities. Normalization itself produces an output model, and we'll look at applying that to some unseen data. We'll also look at the inverse of normalization, which of course is denormalization. So let's look at a simple process. So I have a process that makes some data, doesn't matter about the details, and it's passed to a normalize operator. You'll notice some other operators here. I'm going to use them later, so they're commented out for now. So firstly we'll look at the parameters to the normalize operator. So the first few are really to do with selecting the attributes. I won't cover these in detail, these have been covered elsewhere. I'm basically going to look at all of the attributes, and the data as it happens has no special attributes in it. Let's quickly look at the input data. So it's very simple. It has @1, @2, and there are 1,000 rows, and you can see some statistics about it here. So I'm simply going to select all of these attributes using the parameters to the normalize operator. Here they are. And the important parameter is this one called method, which is Z transformation. There are 4 possibilities here. Z transformation is the first. If I let this now run, it will output the transform data and the original data set. So now, this is the original. If we just familiarise ourselves with the data, we can see that the original input data has been arranged by me to have a minimum and maximum between 1 and 4, and has an average like so and a deviation like so, and you can see that there's basically a lot of data near the origin for @1 with an outlier, and the same is true for @2, but it's a different shape data. If we look at the normalized data now, this is the Z transformation. What this does is to scale and transform the data so that the average is 0 and the deviation is 1. And you can see now that the data has changed to have different minimum, maximum. If I show these look the same, they're the same shape as the data in the input data set. All that's happened is that the descriptive statistics have changed. Now the significance of the Z transformation is it lets you look at a glance, really, see at a glance whether a data point is an outlier or not. And by scaling it so the average is 0, certain modelling techniques work better. So look at the data. Now the normalised data, you can see that @2 and @1 have very large numbers, and you can interpret these as standard deviations away from the mean of 0. So going back to the data, the statistics view here, the data has been arranged so that all the data points have a deviation of 1, so that essentially means that 67% or so of the data is plus or minus 1 from 0, 95% would be plus or minus 2, and something like 99.9% is plus or minus 3. So any data points that are more than that outside that range should be perhaps regarded as outliers. So you can see, if we look at the chart view, let's look at the chart view now in the normalized data @1, and you can see that the data centered around 0, which is this point here, but there's one massive outlier for @1 at 28 or so. @2 similarly, the data is centered around 0. It's a different shape distribution, So now the outlier is at 5.5. So it's still an outlier, but it's perhaps, because of the shape of the distribution, it's not such as a massive outlier, although 5 standard deviations is a long way from the mean. Okay, so that's the Z transformation. Let's change this now to be the range. Now when you set it to range, you can choose a min and a max. Default is 0 and 1, we'll keep it at that. I run it again. What we'll see now is there's the original data, plus 1, from minimum of 1 to maximum of 4, with an average and standard deviation. You can see the two attributes there. If I go to the normalized view, now the data is between 0 and 1, and the average is suitably calculated. And you can see now it's perhaps less easy now to determine that there is actually an outlier, because this is no longer scaled using the Z transformation. But certain investigations force you really to have values between 0 and 1. So obviously this transformation can be useful. Let's go back to the normalize view and let's change this to proportion transformation. Now this is again, this is the input data, 1, 4 average deviation. Now, very different. The shape of the data is obviously the same, but now the scales are different. What is actually happening here is that each value is being divided by the sum of all values. So we could, if we had the time, calculate the sum of all of these values, but essentially what's happening is that you can consider each of the values in the data now to be like a probability that particular value happened. So that can be useful sometimes. And then the final one, let's look at interquartile range. So this uses the middle 50% of the data as an upper and a lower bound to scale the data by. So if we can look at the data, the same shape, and you can see it's sort of like the Z transformation in that it's indicating data that's outside the norm, and you can see that the data points, the outliers, there they are. Those are the outlier points. They've been given values now, which are essentially reflective of the fact that they're outliers. And this is essentially what the interquartile range method gives you a certain possibility of detecting, just by simple inspection of the values of an attribute after transformation. Okay, so now let's go back to Z transformation. Now the output from the normalize operator is in fact a model. It's actually a pre-processing model. If I run that, we can have a quick look at that. There it is, and it's basically telling you some information about the attributes that it saw and what the values were for various descriptive statistics. And this model can be applied to data in general. So by doing this, and this happens to be a subset of some data which is similar to the data used to make the normalize operation in the first place, we should be able to show it working. So what I've done is I've made a copy of this data here. It's 100 examples, and I'm applying the same normalizing operation to those 100 examples as were applied to this 1000 examples here, and the output will appear here, and we can compare it with the original. Okay, so what I'll do is I'll run this again. I'll set a breakpoint just before, and well, I'll do one after just to keep it simple. So I've run this now. We'll see this is 100 examples with these descriptive statistics. So min, max 1.028 to 2.383 from at 2, between 1 and 1.191. And what we're going to do is apply this transformation to it, this normalizing transformation, and we will get a different set of data. All that's happened here is that the the min, max, average and deviation have changed as a result of a scaling and transforming operation. So that's relatively straightforward to do. Important point that normalizing is a model, and you have to be quite careful sometimes to ensure that if you're normalizing training data, you're essentially contaminating all future data with averages based on training data. So you have to be quite careful sometimes not to accidentally introduce some information about the training into the scaling operation you might apply to test data. Having said that, it's still obviously important to do normalization sometimes if that's been applied to the training data to make a model. So that's one gotcha. Let me just do that. Right, now the final thing is we'll cover denormalizing. So what I'll do is I'll just eliminate some of these. Denormalizing, what you do is you take the model and you invert it and you turn it into a denormalizing model. This model can then be applied to test data. So if I do this, what I've done is I've normalized some data and changed the normalizing model to a denormalizing model, then applied that denormalizing model back to the normalized data, so I should get back the original data. So if I just run this, we should see no difference between the original from here and the denormalized data. So if I flick between these, hopefully you can see indeed there's no difference at all. So essentially the denormalizing has undone the normalizing operation. The normalizing was Z transforms. It's been reversed. So the original shape of the data, min and max between 1 and 4, has been recovered. Okay, so sometimes you need to do that if you want to turn your normalizing data. If you want to turn your normalized data back into something a person might relate to or understand. Okay. So finally then what I'll do is I will eliminate all but the simplest view here and just run the Z transformation once and flick between the transformed original data so you can get a view as to what's going on. This is the original data. Those are its statistics. There's the shape of the data, normalized data, statistics, shape. Go backwards and forwards between them. Okay.